Okay, so a crucial point that we've already discovered is that the moment of inertia, the resistance of a rigid body to changes in its angular velocity, depends crucially upon which axis you are rotating that object about. So for instance, if we rotate it about a horizontal axis like this, passing through the center of mass, we'll get some moment of inertia. But if we rotate it about an axis, say, passing through the end of the rod, we'll get a very different answer, and usually say a bigger answer, compared to the center of mass, right? So we want to now talk about this thing called the parallel axis theorem. It's a very powerful theorem used in calculating moments of inertia and so on. And the idea is this: if you know the moment of inertia for rotation of an object about some axis that passes through the center of mass, say this axis passing through the center of mass, then the parallel axis theorem will tell you immediately what the moment of inertia is for rotating about any other axis that's parallel to this axis. Say, for example, slide this guy parallel to here and rotate it about the end. Okay, so it's a very powerful theorem, and it's also very interesting. Okay. And the way we're going to get at that theorem is we're not going to derive it in general. Okay, what we're going to do is we're going to consider a simple example, and that example is a thin uniform rod, like this rod over here. And we're going to calculate using calculus, because that's generally how moments of inertia are calculated, is using calculus. And we're going to calculate the moment of inertia for an axis passing through any like a vertical axis passing through any point along the length of the rod. Okay, that'll be a general result. And then from that, we'll be able to show how the parallel axis theorem works in this particular example, and then we will just generalize and realize and just say, yeah, this is true in general. Okay, so let's go. So if you don't know calculus, don't worry. Just marvel at the power of calculus and use this as motivation to learn calculus really well. Okay, and if you do know calculus, that's great. Then you can see how moments of inertia are calculated. Okay, at least say in these sort of simple one-dimensional examples that we're talking about. Okay, so we've got a thin uniform rod. Let's draw it here. Okay, and so this rod is a uniform, and it has length L and mass M. Now, so the center of mass of this rod is, of course, located right here in the center. That's the center of mass. Okay, and now what we want to do is we want to calculate what is the moment of inertia for rotating this rod about a vertical axis, so twisting it like this, either through the center of mass or in fact anywhere along the length of the rod here. Okay, so we will pick we will put the axis, say, at this point over here. Let's put it over there. Okay, so the axis that we are going to be rotating it around is located a distance a distance d from the center of mass. Okay, and that d can range from 0 up to L over 2, half the length of the rod. Okay, and so we're going to need these two distances. We're going to need this distance, which is obviously equal to L over 2 minus d. So this is L over 2 minus d. So it's half the length of the rod minus d is that distance. And we're going to need this distance, okay, which is equal to L over 2 plus d. Okay, and what else do we need? Now we're going to be rotating, we're going to be grabbing the rod here and twisting this way, applying a torque in that direction, okay, which means a twisting force like that. Right? And we're going to be asking, what is the resistance of that object to changes in its angular velocity for rotation about that axis? Okay? So now, in general, what we know is if we have, say, just the simplest, remember the simplest rigid body is a mass m located at a distance L from the axis of rotation, and the moment of inertia of this guy is equal to m times the perpendicular distance squared. Okay? So if we have a number of masses, if this thing is made up of a number of masses, what it is the moment of inertia is equal to a sum of the individual masses, break that object into a bunch of masses, times xi squared. Okay? So, so let's write that down. So I, the moment of inertia, am I going to run out of room? Let's put it here. Okay, so I, the moment of inertia, just sort of for discrete masses, the sum of masses, is going to be the sum of the individual mass making up that rigid body times the square of the perpendicular distance of that object, say this distance or this distance or this distance squared. Okay? And so in the case of for point particles or discrete particles making it up, it's a sum. For the case of a continuous distribution of mass like this, it becomes an integral. Okay? So how do we do this integral? Well, let's break this long rod of length L into a whole bunch of short pieces. Okay, so this is a little short piece here. And that short piece is of width dx. Okay, so this is like the x-axis here. And we have an infinitesimal width dx. And so the question, first of all, is what is the mass of this little chunk of rod of width dx? Well, the mass of it is going to be take dx, that little width, divide by the total width of the rod. That's the fraction of the total rod we're talking about, times its total mass. Okay? Dx over L times m. That's that mass. And then what we want to do is we want to take that mass and we want to multiply by its perpendicular distance from the axis of rotation, and then we want to square it. So we want this distance and we want to square it. And so we can call this distance x, starting x equals 0 here, up to x equals L over 2 minus d. Okay, so we just do it this way. We just say dx divided by L times m. That's the mass of that little chunk of rod. And then how far away is it from the axis of rotation? Oh, it's just, we're going to call that variable x. Okay, so it's x, and we square it. And then we're going to integrate. We're going to sum over this little mass, this little mass, this little mass, and so on. And we're going to sum from x equals 0 all the way up to x equals L over 2 minus d, because the last chunk of mass is a distance L over 2 minus d, perpendicular distance from the axis of rotation. So we sum x from, that's a dx there, so we're integrating over x from 0 to L over 2 minus d. Okay, so that takes care of the masses on the left-hand side of this axis of rotation. And then we just repeat the game for the masses on the right-hand side of the axis of rotation. So we add to that, breaking this guy up in the same way. We say dx divided by L is the is the width of that little section times the total mass. So that's the mass of that little chunk over here. And then times the distance, perpendicular distance from the axis of rotation, which again we'll call the variable x. And x will range from 0 all the way out to L over 2 plus d. So, so times x squared, from integrating x from 0 out to L over 2 plus d. Okay, so we get that. And so then the moment of inertia for this rod rotated about this axis, a distance d, perpendicular distance d from the center of mass here, or a distance d from the center of mass, is equal to, so in here we have an m over L, that's a constant that we can pull out of the integral. So it's m over L times some stuff. And that stuff is the integral of dx, it's the integral of x squared over x. The integral of x squared is x cubed divided by 3. So it's x cubed divided by 3, evaluated between the two limits, 0 and L over 2 minus d, plus the same thing, m over L times the integral of x squared is x cubed divided by 3 between different limits now, between 0 and L over 2 plus d. Okay? So that's how you would do that integral. And so what you get is m over L. So when we evaluate at the bottom limit, that's just 0. So we just need to evaluate at the top limit. So it becomes, well, let's actually take the 3 outside. So it's m over L taking this factor of 3 outside. It's just x cubed evaluated at L over 2 minus d. So that's L over 2 minus d cubed plus L over 2 plus d cubed. Okay, so it looks like that. And so I'll let you do the algebra. It's trivial. It looks like you have, yeah, it's trivial. Just do that algebra. Okay, and so then certain terms cancel out because there's a minus in there and there's a plus in there. Some terms cancel out. And what you end up with is that the moment of inertia for rotating this rod of mass m, length L, about an axis that is a distance d away from the center of mass, turns out to then be 1 over 12 times ml squared plus m times d squared. Okay? So calculus will allow you to then figure this sort of thing out. Okay? So now what we want to do is, whether you know calculus or not, let's just accept this result. Okay? But it's good to know where results come from, of course. Great. Now we're going to apply that result, which is general. The variable d there is arbitrary. D could be 0 or d could be L over 2. We could range from there to there. Okay, and so let's take two extreme examples. We'll take the two examples, d equals 0 and d equals L over 2, and let's look at those. Okay, so what this thing says is that if you take a rod like this and you rotate that rod about the end like this, what you find is that the moment of inertia I is equal to, so now in this case, the distance d is equal to L over 2. The distance d from the center of mass is L over 2. So in this formula, we stick in L over 2. So L over 2 squared, we're going to get an ml squared, we're going to get a quarter ml squared, plus a 1/12 ml squared is 4/12 is 1/3. So we're going to get 1/3 ml squared. Okay, and now let's compare that to the case where we have exactly the same rod and we're rotating about a parallel axis, but not here, but passing right through the center of mass. Okay, so we're doing that. So the moment of inertia in this case, so d now is equal to 0. So in our formula, we've moved the axis of rotation right through the center of mass. D is equal to 0. We get 1/12 ml squared. So the moment of inertia is equal to 1/12 ml squared. Okay? Now, this moment of inertia, because we have an axis passing right through the center of mass point, this moment of inertia is usually given a special symbol, a special subscript, center of mass, ICM. So the moment of inertia for rotating a rod about its center of mass, like this, okay, is 1/12. Is 1/12 ml squared. However, the moment of inertia for rotating the rod about the end of the rod is a lot more. It's 4 times as large. Okay, 4 over 12 is 1/3. It's 4 times as hard to get this thing to change its angular velocity. Okay, requires exactly 4 times as much torque to get exactly the same angular acceleration. Okay, so great. So, and then we notice something. So we've considered sort of this special case over here. And if we look at this formula for I, what we see is we can rewrite this formula for I as the moment of inertia is equal to 1/12 ml squared. Oh, that's ICM. So it's the moment of inertia for rotating about the center of mass, right over here, plus this other term, md squared. Okay, so this is a result that we derived for this particular example, but this result applies in general. This is a result that's true in general, and it is called the parallel axis theorem. Okay, So let's think about this for a second here. So what does it mean? Okay, so I'm going to draw a picture of a generic rigid body, and we'll understand where these two terms come from, and it's really quite interesting. Okay, so what it says is this. Suppose I have my usual generic rigid body looks like this. And let's suppose that the center of mass of that rigid body, actually let me draw it a little bit tilted, become a little clearer. Okay, so I'm going to, okay, like that. Sorry. Space is always an issue. Let's move this thing over here a little bit, because we got to draw 3 of them. Okay, so this is the original situation. And the idea is the center of mass is located here, let's say. Sure, let's put it there. Suppose the material is more dense over here than it is over here. Okay, so the center of mass is located there. And what we want to do is we want to rotate this object about an axis that is a perpendicular distance d away from the center of mass point there. This is a perpendicular distance d away from the center of mass. And the total mass of this object is m. And we want to rotate it about this axis. And the question is, well, what is its moment of inertia about that axis? Well, I don't know. What this theorem is telling me is it's equal to the moment of inertia for rotating the object about a parallel axis that passes through the center of mass. So it looks like this. Here's the center of mass point. Okay, so take this axis over here and shift it over parallel. It's called the parallel axis theorem. Shift this axis parallel to itself so that it now passes through the center of mass. Okay, so this is a parallel axis. Okay, passing through the center of mass point. Okay, so now I am grabbing it at the center of mass point and twisting like this. What's the resistance to changes in its angular motion? Okay, so that's that. So this is ICM. This is I is equal to ICM plus, now there's this additional term that's interesting. That additional term says, given this original axis of rotation here, so this axis is this axis. And what we do is we repeat this line over here, and we imagine our elemental rigid body, which means a point mass, in this case, equal to as if all of the mass of the object were concentrated at a single point, the center of mass point. So we have an object of mass m sitting right at the point mass of m sitting at the center of mass point, and it is located, and we're trying to spin that thing on a massless rigid rod that is a perpendicular distance d away from the axis of rotation. So we're spinning like this. Okay, so this is, so clearly the moment of inertia of our elemental rigid body, a mass m located at perpendicular distance d away from the axis of rotation, is just md squared. So plus md squared. Okay, so there you go. So, but why is that result true? So, I mean, so what? We calculate this thing and we get this result using calculus and yay! But the point as physicists is to understand intuitively why this is obvious, okay? So this is where it gets cool. Okay, so you need to think about it this way. You need to think about this. So what we're doing is we are taking an object, say, I'll do it this way. We're taking an object and we are trying to rotate the object, say, about the end like this, okay? Counterclockwise about an axis passing through its end. And what this thing is saying is that the moment of inertia for doing that, like how hard is it to do that? Well, it's equal to as hard as it is to do this, rotate through the center of mass point, plus take this entire block and make it a point mass and connect it with a massless rigid rod and try to swing that thing around. So why? Why is that true? Well, if you think like this, it becomes obvious. You say, well, what is the motion involved? Suppose that I rotate this rod through an axis that at the bottom of the rod here like this. So watch this motion carefully. This motion consists of two separate motions. It consists of this motion, taking the center of mass around a circle like this, okay, without rotation, plus rotating on the spot like that. Because I'm doing this, right? So I'm moving the center of mass around, but at the same time, I'm rotating the object around once like this, okay? So, so you need to account for the moment of inertia. How difficult is it, to accelerate a point mass, just to accelerate this thing around? Okay, if there's a massless rigid rod connecting from here to this point over here, and I twist like this, how hard is it to do that? How hard is it to get this thing spinning faster and faster? Okay, so that's that term there. And then on top of that, you have the object also goes once around like this. And so it's actually, spinning faster and faster around like this. So what's the moment of inertia for that rotation? Well, that's the moment of inertia for rotation about the center of mass. And so you can understand intuitively why the parallel axis theorem is true, right? Because in physics, the whole point is to understand everything, right? It's not to memorize formulas. Oh, this is the parallel axis theorem, and know how to apply it. Anyone can learn a formula and learn how to apply it. As a physics student, what you want to understand is intuitively, well, why is it true, right? So that it's sort of obvious, and you don't even have to memorize it because it's obvious to you why it's true, right? You just say, oh yeah, well, it's just that. Right? So anyways, this is a really cool theorem, the parallel axis theorem, and it really sort of deepens your sort of intuitive understanding of this whole idea of moment of inertia. It's a very, very rich topic. Okay, wait. Before we leave this really sort of powerful result, the parallel axis theorem, I want to apply it in two very important examples. The case of a ring and the case of a disk. Uniform ring and uniform disk. So the idea of a ring is we have an object of mass m, and that mass is distributed in the shape of a ring of radius r. Okay, so it's very much like a bicycle tire. Okay, so it looks like this. So the mass is located all the way around in a uniform ring like this of radius r. And so we can imagine this is a bicycle tire with spokes coming into the center here, so that we are able to, grab the axle of the wheel there and exert a twisting force and get a sense of how much resistance this object presents to changes in its angular velocity. Okay. Now the important point about a ring is all of the mass of the object is located as far away from the axis of rotation as possible, which means that the ring actually has the largest moment of inertia possible. Because remember, it's this, for the elemental rigid body, what we've got is a mass m located at a distance L away from an axis of rotation, and the moment of inertia is m times L squared. The further you move that mass away from the axis of rotation, the greater that mass contributes to the moment of inertia. We've taken the entire mass of this object and moved all of the mass as far away from the axis of rotation as possible. Okay? And so what is the moment of inertia in this case? So the moment of inertia for rotation about the center of mass, excuse me, we can just guess this result just by looking at it. So what we do is, so we're rotating about the center of mass. Obviously that's the center of mass point. And so we have an axis passing through the center of mass. What's the moment of inertia for rotation about that center of mass point? And so we can guess the answer immediately, because what we do is we take this, this ring and we break it up into a whole bunch of little chunks of mass. Okay, and so the moment of inertia for this little chunk of mass is ml squared. So it's this mass times the radius r squared. Okay, and then we add the moment of inertia for this mass. Well, it's this mass times that same radius squared, plus this mass times the same radius squared, and so on. So the whole thing is just the total mass times the radius of the ring squared. So it's just equal to m times r squared. Okay, So if you understand this idea of this elemental rigid body here and this idea of ml squared, then you can apply it immediately to the ring and think about it for a second and realize, oh yeah, it's mr squared, without doing any calculus or anything like that. Okay, so that's great. But now we ask the question, well, suppose that rather than rotating this bicycle wheel about the center of mass, let's rotate it about an axis that is parallel to this, parallel axis theorem, on the edge of the wheel. Okay, so now we've grabbed the wheel at the end and it's swinging around like that, right? And so, so the distance from the center of mass, the perpendicular distance from the center of mass to our new axis of rotation is r. Okay, so now the moment of inertia for rotating a bicycle tire about the edge, a point on the edge of it, around an axis parallel to the original axis passing through the center of mass. So that we'll just call that I. So that's supposed to equal ICM plus m times d squared. In this case, the total mass of the wheel is m, and the distance that the axis is from the center of mass, that parallel distance, is that distance d there, is just r in this case. Okay, so d squared is r squared. And so you can see, well, mr squared is ICM, so it's twice ICM. So what you learn immediately is that for taking a bicycle tire about the center of mass, some moment of inertia, to rotate it about the end, it's just exactly twice. Okay, so very powerful theorem. So let's look at another example, which is really useful, especially in comparison with the ring, and that's the uniform disk. So again, this disk is going to have exactly the same mass as the ring, and it's going to have exactly the same radius of the ring. What's different is the way that we've distributed the mass. In this case, all of the mass was as far away from the center, from the axis of rotation as possible, so we should get the maximum moment of inertia, mr squared, in that case. But if we take a disk, so this is a disk of uniform thickness, all that kind of stuff, and this is the center of mass, obviously, here. And so we are, if we try to rotate this disk around an axis passing through the center of mass, we'll get some answer. Okay, and so we can get that answer by doing calculus in the same way as we did for that long rod. We broke that rod into little sections like this and worked it all out. We can take that disk and we can break it into sections. We can use calculus to get the answer. However, one thing that should be clear is that the moment of inertia for rotation with the center mass of the disk should be smaller than the moment of rotation of the center mass, around the center mass of the ring. Okay, that's because in this case, all of the mass was as far as possible from the center of mass, from the axis of rotation. Here, some of those masses are as far away, okay, as in this case, but some of them are closer. And it's this ml squared that's super important. If you come only halfway in, like compare that mass, the contribution of that mass to that mass, well, this mass is halfway in, so the distance is 1/2. 1/2 squared is a quarter. So so this mass, if it's located here, it'll contribute like the ring. But if it's located here, half the distance out, its contribution to the moment of inertia of the disk is only 1/4 the value it would have compared to the value it has if it were at the edge of that disk. And so clearly, the moment of inertia for a disk of the same mass and same radius must be less than mr squared. And if you use calculus, what you get is it's equal to 1/2 mr squared. So that should be intuitive, okay? You should understand this idea really intuitively. Okay, so great. And then the final thing to do is, well, let's suppose now we take that disk, that same disk, and instead of rotating about an axis passing through the center of mass, we're going to do the same thing like we did with the bicycle tire there. We're going to rotate it about an axis passing through the edge of the disk. And so we have this disk going around like this. Okay, how hard is it to get that disk getting up, giving it angular velocity. Okay, and so we just use the parallel axis theorem. So the moment of inertia for rotation about the edge of the disk, well, it's equal to ICM, okay, this ICM, whatever, we have a half mr squared, plus m times d squared. So m is the entire mass of the object concentrated at the center mass point. So it's m times the perpendicular distance from the axis of rotation to the center of mass point. So that's equal to r in this case. So r squared. And so ICM here, excuse me, so mr squared is twice ICM. So it's twice ICM plus ICM is 3 times ICM. Okay, and stuff like that. So you can see how to apply the parallel axis theorem, and you see how powerful it is. But the key thing here is the moment of inertia of an object depends not only on the mass of the object and the size of the object, it depends upon exactly how that mass is distributed. If all that mass is far away from the axis of rotation, it's a large moment of inertia. If all that mass is close to the axis of rotation, it's a small moment of inertia. That's the crucial point here. Okay?